In the previous chapter, we were looking at how to relate forces and velocities without considering acceleration. And this simplified our life for a lot of different types of problems. But now we're going to look at a method that also includes time. So now it's going to relate forces, velocities, and time without considering acceleration. And this method is really useful for impulsive motions. So motions that have a high force for a short amount of time. So this method is great for impulsive. These are usually like greater forces over a short time. And we get to the equation in the same way that we did before, except now we integrate with respect to time. So if you think of our equation of motion, which are force equals ma, but this time we'll write out our acceleration as the derivative of velocity with respect to time. So this is equal to this would be dv over dt. dv over dt. Oh, time is not a vector. And now we bring our time variable up to the other side, so we're left with f dt is equal to m dv. Now we integrate both sides. Remember that the force could be changing with time, so we need to leave it inside the integral. But the mass in this course is never changing, so we can take it out of the integral. And I'm going to integrate from v1 to v2. So when we rewrite this, I'm just going to move the screen up. When we rewrite this, we have the integral of the force dt is equal to the mass times the second speed, or this is still a velocity, sorry, minus mass times v1. And if I just rearrange this, you end up with the mass times velocity 1 plus the integral of f dt is equal to the mass times the second speed. So what this equation is saying, and mass times velocity, we can call this linear momentum. Mass times velocity is the linear momentum of your particle. So this would be linear momentum 1. Over here we have linear momentum 2. And right in the middle, this is considered the impulse. Oh. So the impulse is that force times the time. So what we're saying is that the initial momentum of the particle plus the sum of all the forces applied to the particle during that moment of time is equal to the momentum of the particle at time 2. Keep in mind here that these are all vectors. So when we're doing the math of these problems, we're going to break them up into components. So we'll have mv1x plus the integral of fx dt is equal to mv2 in the x direction, and then mv1y plus the integral of fy dt is equal to mv2y. So whenever you have vectors, you break them into components. Now for this chapter, for momentum, we will only do rectangular components. So only rectangular for this unit. don't have to worry about polar or normal tangential for impulse and momentum. The units here, we have a force times time. So our units here will be force, which is in metric would be newtons times time seconds, or if you're in imperial, it would be pound seconds. You have to consider all of the forces, not just the forces before we were just considering forces in the direction of motion. You must consider all forces. So I'm going to add this here. And your impulse needs to produce movement, because if it doesn't produce movement, then this hasn't changed. The impulse is really affecting that movement. So your impulse must produce movement. I'm going to move the screen up here. There's different cases. So it's possible that your force is constant. So let's say if we plot the force here over time, the force is not changing with time, so it would just be a straight line across here. In this case, the equation for your impulse simplifies to whatever that force is, so let's call this force naught, times your time interval, so t2 minus t1, and you can simply multiply it. But be careful, because the force isn't always going to be constant. In this case, the impulse is now the area under this curve. Can you see that? Because this would be F, which is this, times the change in t, which would be this, so it's the area under the curve. But you can also have a force that's not constant, so variable force. In this case, the force is changing. This is the force. So now you have to make sure that you integrate that impulse is equal to the integral of the force with respect to time. It's still the area under the curve, but now you have to capture the area under the curve that's not a rectangle. There's also what we call impulsive forces. And even though they're called very similar, impulsive forces are specifically large forces over a very short time. So a good visual for this would be a tennis racket hitting a tennis ball. It hits the ball for a very, very short time. Now, realistically, the force against the ball when the racket hits it is not constant. It's going to be changing with time. But because this time interval is so short, we actually just consider it as if the force was constant. So to simplify problems, we consider the impulse force remains constant. In which case, we can use this equation here, where you're just multiplying the force times the time interval. The most important thing to know when you're dealing with these large impulsive forces is that they actually allow you to also ignore other forces. So the impulsive effect of a force is so large that we ignore non-impulsive forces in those questions. So ignore non-impulsive forces. And these are your weight and or spring forces. because let's say the tennis ball weighs 0.5 newtons. The force between the ball and the racket will be between 200 and 400 newtons. So it really makes sense to ignore the force due to the weight of that ball. And then you can also neglect, there might be another impulsive force that's super small, you can also neglect that. The last thing I want to mention in this video is the conservation of impulse and momentum. So I'm going to move the screen up again. So for conservation of impulse and momentum, and this is really when you have systems of particles. So if the sum of external forces acting on the system of particles is 0, or if there's no external force, then you can simplify the equation essentially. You take out the impulse component, and what you end up with is the sum of linear momentum 1 is equal to the sum of linear momentum 2. So here, this is saying all of the linear momentum at the beginning of all the particles is equal to the linear momentum of all particles at the end. And then implied in here is that internal forces are canceling out. So let's say you have, and we'll do this example in the next question, but let's say you have a cart here that's on wheels and it's stationary, and you have a bag that gets shot at it, and you have a bag kind of lands in the cart here and makes the cart move. All of the linear momentum from the bag, because the cart is not moving to begin with, so all of the linear momentum of this bag coming in will be conserved, and that is what will make the cart and trolley move afterwards. So that's the example that we'll solve first, so that you can get an idea of what's happening. One more thing I don't think I mentioned yet is you have to make sure that you're drawing diagrams. So in all of these chapters, we've been drawing diagrams, but your diagram has to match the equation. So in this chapter, we have mv1 plus the impulse. It's either the sum or the integral of the force delta t is equal to mv2. So this is the same equation I had earlier, but here I've written this out as the sum instead of the integral. In this case, you have to do a drawing of this equation. Your drawing is always representing your equation. So in this case, you would have your mv maybe going like this. Then you would draw here your forces. You'd have all your forces on your particle times your delta t. And then this would be equal to whatever the linear momentum was afterwards. And we'll also get into that in the next video.